In this video, we're going to explore quadric surfaces. These may also be referred to as quadratic surfaces. A quadric surface is one that is described by a general second-degree equation in three variables. It will look something like ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus j is equal to 0. This is a very general form, and the coefficients, which are constants, will not all be equal to 0. There are a huge variety of quadric surfaces that we could develop using various combinations of the terms in this general second-degree equation of three variables. But we are only going to focus on a few of the more common quadric surfaces. So the standard quadric surfaces we're going to work with will include the ellipsoid, and the standard equation for this one looks like x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. All the traces for an ellipsoid will be ellipses, and the graph of the ellipsoid is shaped like an oblong lozenge. You'll notice that the quadric surfaces that I'm working with will all be centered on the origin of my coordinate system. I might have an elliptic paraboloid. The standard form of this equation looks like z is equal to x squared over a squared plus y squared over b squared. Traces where z is equal to z naught are ellipses, and traces with x is equal to x naught and y is equal to y naught will be parabolas. The graph of this looks like the top of a wine flute. I might have an elliptic cone. This has the standard equation form x squared over a squared plus y squared over b squared is equal to z squared over c squared. Traces where z equal to z naught are not 0 will be ellipses. Traces with x equal x naught or y equal y naught will be hyperbolas or intersecting lines. This graph looks like a pair of napped cones where the points of the cones meet at the origin of my coordinate system. Additional standard quadric surfaces include the hyperboloid of one sheet. This has an equation of the form x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. The features here have traces where z is equal to z naught that are ellipses for all z naught, and traces where x is equal to x naught or y is equal to y naught will be hyperbolas. The graph of this resembles an hourglass or a cylinder that's been pinched in the middle, with the waist centered at the origin of my coordinate system. Another quadric surface will be the hyperboloid of two sheets. This equation has the standard form negative x squared over a squared minus y squared over b squared plus z squared over c squared is equal to 1. Traces where z is equal to z naught, where the absolute value of z naught is greater than the absolute value of c, will be ellipses, and traces with x equal x naught or y equal y naught will be hyperbolas. The graph of this one looks like two opposing hyperbolic dishes or satellite dishes that are centered at the origin of the coordinate system. Notice that the hyperboloid of one sheet forms a continuous surface, while the hyperboloid of two sheets have two distinct surfaces. And I can have something called a hyperbolic paraboloid. This has an equation that looks like z is equal to x squared over a squared minus y squared over b squared. Traces with z is equal to z naught, where neither z or z naught are equal to 0, are going to give me hyperbolas, while traces with x equal to x naught or y equal y naught will give me parabolas. The graph of this hyperbolic paraboloid looks almost like a saddle with a very high front and back on it. I want to work some examples. If I'm given the quadric surface described by the equation y is equal to x squared over 16 minus 4z squared, I want to identify the intercepts for each coordinate axis when they exist, and I want to find the equations of the xy, xz, and yz traces when they exist, and sketch the graph and identify what the surface is. The first thing I'm going to do is recognize that my x, y, and z intercepts will occur when the other two coordinates are 0, so that the x-intercept occurs where y and z are both 0. I plug those values in, and I get 0 is equal to x squared over 16, which means x has to equal 0. The y-intercept happens when x and z are 0. Plugging that in, I get y is equal to 0 minus 0, which says that y is equal to 0. And the z-intercept is given when x and y are 0. Plugging 0 in for x and y, I get z is equal to 0. So that my intercepts all occur at x is equal to y is equal to z is equal to 0. The xy trace is when z is equal to 0. Plugging 0 in for z, I get y is equal to x squared over 16. This gives me a parabolic xy trace. The xz trace is when y is equal to 0. I plug 0 in for y. I get x squared over 16 minus 4z squared is equal to 0. This means that my trace is a hyperbola. The yz trace is when x is equal to 0. I get y is equal to negative 4z squared. These traces will be parabolas. When I graph it, I get a hyperbolic paraboloid that is centered at the origin of my coordinate system, and it resembles a saddle that lies on its side. In example 2, I have a quadric surface given by the equation negative x squared over 6 minus 24y squared plus z squared over 24 minus 6 is equal to 0. I want to find the x, y, and z intercepts when they exist, and the equations of the x, y, x, z, y, z traces when they exist, and then sketch the graph and identify the surface. My x-intercept is when y and z are 0. I get 0 is equal to negative x squared over 6 minus 6. This gives me x is equal to the square root of negative 36. This is not a real number, so there is no x-intercept. The y-intercept occurs when x and z are 0. I get 0 is equal to negative 24y squared minus 6, which tells me y is equal to the square root of negative 1/3. There will be no y-intercept. The z-intercept is when y and x are 0. This gives me z squared over 24 minus 6 is equal to 0, which tells me that z can be plus or minus 12. The only axis intercepts I have are two z-intercepts, one at negative 12 and one at 12. My xy trace happens when z is 0. I get negative x squared over 6 minus 24y squared minus 6 is 0. This is not in the standard form of an xy trace equation. There is no xy trace. The xz trace happens when y is equal to 0. I get negative x squared over 6 plus z squared over 24 minus 6 is equal to 0. These traces will be hyperbolas. The yz trace happens when x is 0. I get negative 24y squared plus z squared over 24 minus 6 is equal to 0. These traces will be hyperbolas. When I graph this, I get two distinct hyperbolic regions separated by a gap that is centered at the origin of the coordinate system. This is a hyperboloid of two sheets. Now you get to try it. Pause the video and identify the intercepts for each coordinate axes when they exist, and then find the equations of the x, y, x, z, and y, z traces when they exist, and sketch a graph and identify the surface that is described by the equation 9z squared plus x squared minus y squared over 3 minus 1 is equal to 0. When you're ready, restart the video to check your understanding. I'm first going to find the x, y, and z intercepts. The x-intercept occurs when y is equal to z is equal to 0. I plug in 0 for y and z. I get x squared minus 1 is equal to 1, so that x is equal to plus or minus 1. There will be two x-intercepts. The y-intercept is when x and z are 0. I get negative y squared over 3 minus 1 is equal to 0, or y is equal to the square root of negative 3. There will be no y-intercept here. The z-intercept occurs when x and y are 0. I get 9z squared minus 1 is 0, where z is equal to plus or minus 1/3. There will be two z-intercepts. My xy trace happens when z is 0. This gives me x squared minus y squared over 3 minus 1 is equal to 0. These traces are hyperbolas. The xz trace is when y is equal to 0. I get 9z squared plus x squared minus 1 is equal to 0. These traces are ellipses. The yz trace is when x is equal to 0. I get 9z squared minus y squared over 3 minus 1 is equal to 0. This gives me traces that are hyperbolas. When I graph this, I get a sideways cylinder that's pinched in the middle at the origin. This is a hyperboloid of one sheet. This gives you an idea of the types of quadric surfaces that we'll be interested in. Be sure and let me know if you have any questions about working with quadric surfaces.